Hello everybody and welcome to Handmade Hero Show. We code a complete game live on stream. We are going to probably move up a level in complexity with our lighting today. So what we have done, and I guess I should go ahead and run it here to bring everyone up to speed on where we are. We did a simple test of the ray casting and used it for debugging, and what we have running now, as you can see, is an example where you can move a light through the environment and it will do fairly perfect radial interpolation on surfaces that it does hit, and then a simple binary on-off kind of thing for shadowing, which again is not something we actually wanted. We don't actually want to use that effect in the lighting. It's not something I'm going for. But this was basically a test to ensure that we could get reliable ray casting results. And it seems like we've done that pretty well. So I feel like we're in a good we're in a good place right now in terms of feeling confident that our raycaster isn't completely broken. And it's also running plenty fast enough at the moment. This is not even multi-threaded right now. This is entirely single-threaded that it's running, which is kind of great. And it appears to be running nice and 60-ish. So basically, we're in a good position now to say, let's take the next jump up and start trying to do the lighting a little bit more realistically. This is, again, also computing the lighting every frame rather than using an average over a few frames, which we'd like to do. And so what we want to do now is sort of start to move towards that more complex, more complete solution. And we have, sort of three things we want to do. Two of them, I think, aren't so hard. One of them is potentially hard. So the three things that we want to do, number one, we want to start averaging across frames. We set ourselves up to do this, so that is really just a matter of debugging. We've already pretty much figured out how that will work, and we know what we want to do there. Namely, our voxel is already set up to be able to save across runs, and we will just save the voxel and average it in. The only thing that will be tricky about that is making sure that the voxel copies itself to the correct location during center of simulation jumps. So we have to do that particular piece of the code, but that's the only thing that we really need to do to get the averaging working. So we want to do that. That's number one. And we might just do that right off the bat. That may be the first, because we can do that even with this, right? We could take this solution here and just smooth it over time, and we would see some lag on that shadow, right? And a smoother, a gradual lag on that shadow or something, right? And so you can imagine that averaging step is something that's pretty easy to do, and we could totally do that. The next thing that we have is we've got to do indirect bounce, real indirect bounce and convection. That's a little more complicated, again, but nothing tricky. We already have the raycaster. We already have a way to sample from voxels. So we kind of know exactly what we're writing there. Again, it's not particularly tricky. It's just going to be a piece of code that says, look, when you hit a particular piece of the geometry, you're going to want to look up in the voxel what the lighting is there and put it back, right? And the final thing that we need to do is the one that's really complicated, and it affects both of these things, which is that if we just do a basic addition into our lighting voxel, I don't think we're going to get very good results. We would maybe we'll get okay results, but I think we can do a lot better than that. Because basically our voxel allows us at 60 frames a second quite easily, as we've determined, to interpolate quite a bit of information. And so the other thing that we need to kind of solve, and this is the one that's a much harder problem and much more broad, I think, is how do we best store and update this lighting information? Because we will have a fantastic amount of information coming into the system. Basically an embarrassment of riches in a sense. We will have between 4 to 8, well, I shouldn't say between, 4, 8, 12, or 16, depending on what we can get away with in terms of speed. New raycasts coming in at each voxel, right? Or at each light probe and then spread out to voxels. Let's see how we want to do it. We will have the previous frames complete information. And we will then need to decide how we want to combine those results to create the new lighting for the subsequent frame. And while we know some basic things about it, like, okay, we can obviously mix these together with a simple linear blend that updates it over time or whatever else, right? We don't have to think very hard about how to blend values necessarily, but what we don't know is how are we storing these and how are we distributing them about the voxel and then reconstructing them. What we've got in there right now is essentially like 4 light fields with a normal and an intensity per light field, basically, right? And we know that that's something that can interpolate one light exactly, right? We can do a very good job interpolating a single light source exactly. We proved that by having a perfectly spherical fall off that reconstructed exactly, even though our voxel is not even close to the resolution that would be necessary to do that. So we proved that that field reconstructs exactly per pixel, even though we're not storing it anywhere close to per pixel. But the question is, once we introduce sort of a rich lighting environment where light is coming from everywhere, the floor, the ceiling, the walls, right, it's bouncing around, what is the actual fundamental way that we combine these values, right? And so that's the part that I feel like we don't really know, or at least I don't really know. And so that's the part that I'm not sure what to do about. And so when we look at what we're doing going forward, I think those first 2 things I listed are just a case of rolling up our sleeves and implementing them. There isn't a lot of mystery there. We know what we're doing, and we have basic solutions in place that just need to be like wired up and debugged and improved, right? And that's a good place to be. But what we fundamentally don't know is whether or not what we've got right now for the voxel is the right thing to do, right? Because there's other ways, you know, we basically know our voxel is a way of storing literally 8 4-element things for reconstruction. So we know we have a lot of power there. We just don't know what to do with it. And so we may find that, like, okay, we need to fall back and do something like spherical harmonics or something like this, because it turns out that there's really no way to update 4 light fields in a coherent way, and you need something else to do it. Maybe we need to just figure out like how, ooh, it's feeding time for the puss. You coming for food, puss? The puss is unsure. She's kind of hopping over to the food bowl. She's looking around. And so we don't really know, and that's really, it's unknown things are the kinds of things that that usually take the longest because they take some exploration to figure out. So that's the complete picture for what we're doing this weekend, and who knows how far we'll get on it. But like I said, the first 2 are maybe the ones to start with, because we can we know that we can just kind of get to work on those and produce, you know, some usable code just by like focusing on debugging and improving what we already have. And that's, you know, might as well get that done first because we know we can do it. And then once we have those done, just focus on like, okay, now that we have all the inputs to the system, how do we make the system actually work well? So if we jump over to the lighting, if we go ahead and look at this code, the first thing that you'll notice is that like that test code, we've got it in this thing that's like, where is it? Test cast from probe, right? So this right here. So what we're doing here is we're just, you know, doing literally a piece of test code. We're casting here by clearing the voxel, then stepping through each of the light probes in the system, of which there are many. We're doing a test raycast to the light source. And then in addition to having some debug code in here, which we don't have enabled right now, you can see here that we're basically turning off the test case, but you know, it's there for when we need it for debugging. In the case where we have not hit anything, we spread out the lighting information that we have and call it a day. Now that's not even what we would want to do, even if this is what we were trying to do permanently. We would want to spam out to the voxel, and we would want to put like negative lighting in there if you couldn't see this one, to say that there was a shadow coming in this direction. But again, like, this is not what this was for. This was not trying to reproduce lighting accurately or interestingly. It was just trying to show us definitively whether or not the raycasting was properly working. And we did have a bunch of bugs. It did its job nicely. Like, we were able to find our bugs in a much faster way than if we had tried to roll all this together and been wondering whether the lighting was working or not, and, you know, trying to see from kind of subtle stuff. So what we would like to move to now is the actual lighting calculation here in compute light propagation. So what you can see here is this is set up for multi-threading, and I guess I'm not sure. So is this, how is this compute light propagation work? Ooh, so this, okay, so we basically had this set up to see if we wanted to basically turn it to single threaded is what that was doing. But anyway, this right here, this compute light propagation is what we're looking at. And what the compute light propagation is doing is it's building a bunch of work structures. Those work structures are for multi-threading the lighting. And what you can see is they all kind of will call down to a workhorse routine, which is this one here, which is the actual compute lighting propagation. Now, they should probably be called something different, so it's a little easier to see which one is which, like this, right? And then if I go to compute light propagation, we should probably have that work thusly. So, you know, we can see which one is which. Just makes it a little bit clearer. So anyway, what we want to do here is make sure that that these are working well, and it looks like do lighting work. Wait a minute. So what is going on here with do lighting work? Do lighting work is what exactly? Sorry, we haven't looked at this in a while. Ah, so this callback here, yeah. There we go. So anyway, this, I don't know why we don't just wrap this thing up. Actually, like, I'm not sure why this is doing a separate call out like that. That seems unnecessary. I'm gonna just take a quick look at platform work queue callback just to see what that actually is doing. So it's just a platform work queue and some data. I don't know why it passes the work queue exactly. I don't know if that queue is actually used. Hold on a second. Let's see. So it's not. So if we wanted to, what we could do here is not have this double call, which I think would be better. So what we could do here is just make this itself be the thing we call, like that. That seems a little bit better to me. And then we would get rid of this. And here we would just cast down. So our lighting work, in this case, would just be the data getting cast down, right? And if we did it that way, then this code right here could go away, and we wouldn't have that extra call. That, you know, the compiler is probably going to weld that just fine, but I'm just not interested in having that extra work there. And so here, instead of calling do lighting work, this will be like compute light propagation work, and now we've kind of rerouted that. So anyway, let me just see here. Oops, I don't know what that was about. I also don't know why data is highlighted as a type there. That doesn't make a lot of sense, but I guess there is something that's data. I don't know. Anyway, so if you take a look at what's going on here, we now have our raycaster here, which is just a thing that does raycasting. And we have our compute light propagation work. We've debugged the raycaster. Compute light propagation work is the thing that we haven't really worked on. Now, we used to have it working in the old scheme, and the old scheme did not do voxel-based lighting. So we kind of have to change around the way that it was working in a sense. But in here, we would like to sort of start by taking stock of this routine, figuring out what we're going to have to do to get it to where we want it to be, and then making those modifications. So the superstructure of the routine should still be fine. We're still going to grab a work structure, right? And we're still going to figure out which lighting probes we want to calculate given this work structure. So when we get these light probes and they come into the system here, what we're going to want to do is say, all right, we still want it sliced by work probe, but that's how we're going to distribute the work. So we still want this superstructure to be in place. Now, furthermore, I'm not sure to what extent we need to pre-filter that list, but we'll work on that later. Meaning, right now we're going to do raycasting for the entire light probes and all of the light volume. We can pre-filter that at push time. So I'm just going to assume that we can slice the work up pretty much uniformly, and that we won't have to do any sort of work stealing or figuring out that work actually didn't need to be done in certain places. So I think we can do this pretty straightforward. Also, I feel like I'm hitting the metal on my shirt here. I'm going to take this off. There we go. All right. It was clicking on the metal, you know what I'm saying? I know that's happened before, so I just want to make sure that's not annoying people. So if we look at what's going on here, we're going to cycle over the light probes. And again, we already kind of have our test cast routine. You can see we were doing the same thing here, right? We're cycling over the light probe. So all we're really talking about is to be multi-threaded, we're slicing it so each thread works on a subset of the light probes. That's all that's going on here. Much like here, we're pulling out the cast direction by grabbing whichever light probe it is that we're talking about here. And then what we're trying to do is cast 4 rays at a time. We're just going to cast those rays in directions based on our random table. So what you see here is we're not going to actually target the light source necessarily. I mean, one of the things we might target the light source with one of our ray casts every time or something, or you know, periodically we may check the light source, but since generally speaking we won't exactly know which light sources we even want to target or anything like that, it makes it a little bit harder. So here's what I would say about this. If we assume that we have some set of light sources that are known coming in, maybe we want to loop those in here, but for the moment what we're going to do is ignore that part of it. And instead of having the light sources be specifically targeted off the bat, we'll probably roll that in a little bit later. Or maybe we won't, I don't know, we'll see. Maybe that's something we'll do on one of them, I'm not sure. But what you can see here is we're going to compute a ray origin here, and we're going to compute a ray direction by saying, well, however many rays we want to cast here. This is actually a ray bundle count. But what we're going to do is we're going to grab out 4 rays to cast and go from there. Now, what I think I want to do, like I said, is I think we want to try targeting light sources maybe a little bit more than we have been. And that's just a way of saying, look, we know that we've got a push light call here where we can put lights into the system. And we want to support an arbitrary number of light sources, so we don't want to do anything that assumes there's only 1, 2, or 3 lights. We want to assume that there could be hundreds of lights if we want there to be. But what we'd like to do is say, look, we want a way of targeting the light source occasionally. So what I'm going to do is suggest that perhaps this routine needs to be changed a little bit. And instead of calling this a ray index, right, we're going to call it a ray bundle index. That's just true regardless. And what I would like to do is precede here. What we're going to do is say ray direction is something that will have some startup to it. So what we'll do is we'll say at the start, right, our ray direction will target some light sources. So at the start, we'll fill it with 4 ray bundles that are all designed to like go towards light sources that we know about as a way of sort of introducing a little bit of bias in the system towards hitting a light source. And then in here, what we'll do is we'll take the ray direction when we're sampling this, and we'll just move this to the end, right? And I'm going to get rid of this to do because we're going to take care of that today as well. So after we have done the work on all of our rays, right, what I want to do here is basically update this at the end. And what I'm doing there, right, is I'm just changing sort of the fundamental way that this is working by saying, okay, one of the things that's always free to do in a for loop is update at the end instead of the beginning. And then it's free for you to make the first run of your for loop do something different, right? So in this case, we know we want to pull things out of an array of sampling directions. And in this case, what we're doing is saying, look, the first time we do that, instead of pulling it out, we're going to use some special thing that's not in that array or something like that. And that's how we're going to go with it. So then we have like here our sampling sphere with the sample direction there, right? And then that'll kick in later. And so what we want to do is just say the ray bundle count is going to be the thing that we're using here. I don't think that's actually, you know, this will not necessarily be accurate anymore because if we have one startup one, it means we'd be skipping some in the ray bundle, but you know, you get the idea. So that's something we can do very easily, and I think we probably do want to do that. And that way we can say, well, the ray bundle count is actually, you know, it's maybe this, right? But we would need to pad that sample direction with a fake one at the end anyway so that we didn't fetch off the end of the array. So I think this is still probably roughly what we would be doing. I don't know. We'll see. So anyway, excuse me. We need to set up all these parameters correctly, and we need to get our sampling sphere taken put in as well. The other thing I suppose I could do is write into the sampling sphere itself, like leave a space at the beginning and have it cast. So you know what? I could do that as well. Because I just don't think we want to bother with that. All right, so I think we're going to leave it like this. We'll see. We'll sort of work on it as we go. So anyway, in terms of which direction we're going to be sampling here, you can see our dir sample index here. That's just something that we're using to figure out sort of a stochastic version of the sphere that we're going to use. This is so we don't always cast the same direction every frame, and kind of average over a larger sphere. And so this is that lookup here, and then we're going to, you know, use the particular sphere that we pick out among many of our random spheres that we have. And remember, we've got a thing that's like this sampling spheres that we generated, and these are going to have other information that we need. We're going to have to like update our generator program to do exactly what we need now, but we basically have this code written as well, and we verify that that sphere is accurate. So we're in pretty good shape with that stuff. All right. So what we're going to do is we're going to go through the ray bundles. We're going to basically raycast from the ray origin, ray direction here. And again, we're updating that ray direction every loop through here to a different ray bundle. We're going to go ahead and see what we hit. We're going to compute that this way, right? I don't know. This is actually like a Boolean, like did we hit or not. So I'm not sure why that's called t hit necessarily, but it's fine. Anyway, so we come through here and we go through and do our subrays. And our subrays here just look to see, this is a thing for pushing debug lines. If we want to debug one of them, we can do it this way. But at the moment, we don't really need to worry about that code. So what we're doing here is saying, all right, if we hit, right, so this is the thing that tells us whether or not we hit. If we hit, we're going to try and do a lighting lookup. If we didn't, we're just going to go ahead and put the moon color in there, and that's all we're going to do. And again, this code probably needs to be improved a bit to work with some kind of a notion of localized ambient lighting. You know, because we might want to do something like that. I don't know if we actually need that or not, because in theory, you should always hit something. If you cast upward, you should hit like a dungeon floor or something. But at the moment, we don't really put ceilings on our rooms, so you can see why we may want to. It depends on how we want to solve that problem. If we always put ceilings on our rooms, then this just always kind of works. If we don't, then it doesn't. So we kind of need to have some opinion about that. And if we decide that we don't want to put ceilings on the rooms, then we need to have some notion of localized color that basically says, like, for each light probe, this is what I would want here as an ambient color value in the case where you cast upward and don't hit anything, right? So, you know, basically, we could pretty trivially have it so that if you look at what we're pushing on there in terms of light probe information, in this right here, it would be pretty cheap for us to just store an extra piece of information, which is basically the emission angle or something, and you know, basically a vector that points towards where the ambient light is coming from, if any, and then a color value that should be modulated in. So it would be pretty cheap for us to just have that be a thing. And I don't know whether we want to go that route or not, but that's something we could certainly consider. So again, like, so just something to think about, and we'll decide how we want to tune that lighting a little bit later. The ambient lighting is not super important to us right now, but when we're actually going to kind of finalize the lighting at the very end of this sweep, we probably want to sort of get in there and artistically think, like, what do we want to have happen here? Now, thankfully, this garbage doesn't have to happen anymore. This update for this way that we were updating things doesn't really have to happen, but we do need to do some updating. So let's go through and sweep through this and figure out what we kind of want to do here. So if you look at what happens on the case where we do get a hit, you can see here that we have a probe sample position. That probe sample position is basically saying where are we actually hitting? Like, where did we stop? And then the normal is what was the normal on the surface at the point where we stopped. So this is basically telling us like the surface we hit and its surface normal, so that we can compute how the light should have been moved, right? We also know what the reference color was for that occluder, and that's basically telling us like, okay, what's like the average color of the texture at that point or something. And we haven't really set those up yet. I think they're all basically gray or something, so we will want to go in and tune those as well. But we know that they will come in here eventually, so at some point we will get that piece of information. We then also know what the emission was on that ray, but I don't actually know why we're doing it quite that way. That doesn't really seem like what we want. Because surfaces won't really have emission anymore, I don't think, in that way, because lights are pushed separately from surfaces, so... So I don't really know how we want to treat that. I guess we do, because when we push in lights, they need to basically be boxes as well. So I suppose we do need to do that. The only question is why the sample ref color can't have that included in it. Well, let's continue thinking this through a little bit more, and we'll go from there. So let's see what we need to do here. So in terms of figuring out what the lighting actually is, we're going to have to do a light probe query at this point, right? And the light probe query is going to be some kind of a voxel situation where we do the gather exactly like we would normally do it in the pixel shader and some interpolation between them, right? It's going to be a little bit expensive, but that's basically what's going to happen. And we're going to have to call something like this that won't exactly be this. Let me see if light probe irradiance is still in there. Yeah, it is. So we left this in there, but it's not actually a valid thing. Like, we don't actually want this V3 light 6 stuff. That was for when we were going to do cubic direction stuff, and we kind of decided that we're not storing that anymore. So we wouldn't actually want the light probe irradiance in there, and furthermore, the light probe irradiance like wouldn't go in here either, right? This is not what would actually happen. This is the actual lighting information, and it's the entirety of the lighting information now. So this stuff here, like light probe position is still the case, but light probe irradiance is just not something that's actually there anymore. So we can actually eliminate that entirely if we want to, right? We can actually just get rid of this entirely. And so we're not going to be returning it as something like that, right? Instead, what we're going to be doing is just like, some kind of light value is going to come in here. We're just going to get, how much light should we have actually seen bouncing off the surface or whatever, right? So we're going to want to do something like this, and then we're going to want to do the reflection. So it's hard to say exactly what we would want to do in this case, but we know we've got a probe sample n, so it'd probably be something like this. Like, if you assume that we are bouncing off of this surface, so we know the surface normal, we know what direction it would be because it would be like the reflection vector here. So we'd have to compute the reflection vector around this surface normal, which we can do. What is the light coming in that direction, right? And so we'd want to just do like get compute voxel lighting or something like this. Something like that, I don't know. But we're going to want to basically pass this in where we say, here's our sample location, here's the normal at that location, and here's the vector that we're trying to sample out towards. We may not actually need this. In fact, now that I think about it, we probably don't. We just would compute the reflection vector and then say this is the direction we wanted to know about. You know, that's not really true, because this is diffuse to a large extent, right? And so I guess what we would say is, I don't really know, so I guess we would have to have, since we don't, I don't know if we would need material parameters in here for this. That's really kind of hard to say, I guess. But since we're computing the lighting very coarsely, I would say, you know, we probably just want to assume that surfaces are diffuse. So maybe we'll do this for now, right? So we'll just say, look, here's the lighting location. Here's the hemisphere that it can gather. Tell me what, you know, what do you see? And we'll use that. So then we would go in here and do exactly what we would expect here, right? This is all pretty much exactly the same. I don't know where emission direction was coming from. So the ray direction with the subray in particular, it's saying it's the negative of that. So yeah, that's just doing the cosine fall off is all that's doing, and that's fine as well. So yeah, I mean, that's all okay, I think. And then that's going to give us back what the lighting transfer should have been at that point, right? So given that, we have a couple different things that I guess we would need to do here. And in terms of how to interpolate it all, again, this is the part that I don't really know. So now we get down to the part that I'm not sure how we want to do. It's pretty confusing. So if you look here, this is how we were doing the update before. It's just a straight linear blend that was doing like the sort of an accumulation, where we were just accumulating everything into this accumulator using weights that were specified as part of the sampling sphere. But that's not what we're going to be wanting to do now, right? And this is the part that I don't actually know what we should be doing. We need to spread into the voxel. So here, basically the test test cast or whatever it is. So the test cast from probes, right? You can see that we've got the spam voxel thing happening here, where we just like put forth lighting information into our voxel. What that's doing, right, is just hard writing the result. So it's just writing the result in literally. And like I said, that's not really what we need to be doing long term. We need to be doing kind of averaging. And so the spam voxel part, and in fact this part right here, maybe wants to come out into something a little bit more specific. So this thing is going to be like a spam voxel call itself. So here's our actual spam voxel call. And these are going to be called like spam voxel slice or something, right? And so what we're going to need to do is every time we finish one of these things, we're going to have to spam the voxel with the information. Now, what I would like to do is, since this is expensive, spamming the voxel, I would like to basically accumulate the voxel with the transfer PPS inside this thing, right? And then at the end, spam the voxel. So I'd like to like local accumulate and then spam the voxel at the very end. So it would basically take place out here. So like the spam voxel part would happen here, right? So I'm going to move these up because I want them to be used from the actual lighting code, which is right here, right? There it is. So the spamming of the voxel wants to happen in here, and the get voxel index and that stuff, like this stuff is all kind of garbage. We're done with it now, I think. I don't think we want any of this, actually. So this is all kind of incorrect. There is the UVW part. We do maybe need a little bit of that stuff now, but of course that will happen. That'll kind of happen inside here. So where we're doing this work, we will need one that actually does the UVs as well. And that's just going to be for blending. But we'll deal with that in a second. All right. So I think that's what we want this to look like. So we'll have our spam voxel slice, which does that part of it, and we'll have our spam voxel, which does the other part of it. And so the spam voxel here is just going to say we need the solution and the spam position basically. And so we'll pass cast p to spam voxel, and then it will do all of the spamming here. It needs the test, like all this nonsense, so that it can actually record like whether it's spamming the right place and all that sort of thing. But other than that, it's just a direct pass through. And we probably won't be able to leave it like that forever because it's probably going to be a little too costly to have all of this configurability in there in terms of what the compiler is going to do, because this is pretty much the hot path. Like this is the spiciest path in the whole game. It's the thing that costs the most runtime, so we're not going to be able to do all that ad infinitum, but more or less this is what we're looking at. And we can sort of leave it like this until we go to do our like full performance optimization, right? All right, so let's start cleaning up the compilers and move towards actually running that stuff for real. Here in the irradiance part of things, we want to just get rid of this entirely. It's not anything that we actually need. So I'm just going to get rid of the irradiance stuff. It's just not necessary. Also, set light probe position is now also gone, I believe, because we're just pushing light probes on, not setting their positions anymore since we don't have to store any of that stuff. We can actually also pull the light probe assignment because I'm pretty sure we just don't want to ever have to deal with that anymore. The solution we came up with was pretty much far superior. You know what? Also, I feel like I'm too loud in my headphones. I'm annoying my own self. Can that be fixed? I'm curious. Oh, it does. So it actually affects what I hear. Well, that's annoying. Can't you do something about that? Can't I do something about that? I guess I can't. Oh well. Life goes on. Anyway, assuming that I don't want to ruin my own ears with this, I'm gonna have to figure out some way to fix that. I'm not really sure what to do about that, but we'll look at it later. Anyway, so in the spamming, right? We can now spam from inside the other routine, which is good. And I'm just gonna start cleaning up the compilers on that, and then we also have to actually figure out what we're gonna do for the blending inside the spamming, and maybe we'll use our current test version to figure that out. All right, so we need the array bundle count here. This is something that targets the light source part of things. We can actually use the debug light for that right now if we want to. So if I, inside the lighting code here, take the debug light P, which is, well, in here, here is the information in question. Yeah, so, well, I guess part of the problem too is that it won't actually hit the debug light. Yeah, so we're gonna, all right, so here's what I would propose we do. I would propose that what we need to do is take this in 2 steps. I'm gonna put, so in here I'm gonna take the direction to the light source, right? I'm going to take the direction of light source here and compute that by just taking where the light is and subtracting the light probe P, right? I'm going to seed the ray direction here with just 4 of those, like so. And I don't know that I actually need those to be normalized, but just in case, I'll normalize them here. It won't be expensive. It's only done 1 time out of the array bundles, so it's not too bad. And plus, we're not going to be doing that in general. So what I want to do there is say, look, we have to put the lights into the actual casting space because otherwise you can't ever hit them. And so what I'd like to do here is just say, well, let's go ahead and first of all try to get the lights into the system so that we don't pre-code where they're coming from, and that we can do in our test cast, which will debug that part of it which would save us some time because it'll make it easier for us to figure out where's the enlarge voxel call? There we go. Forgot to put this one with our sort of bundle of things we do. All right. So I think that's what we want to do first, is get the lights into the raycaster rather than having them be outside in the debug thing, and make our test code work with that. So I think that's mostly what we want. Looking through here, what is the actual complaint on this guy? Ray index, it's ray bundle index, that's all. And then spam voxel here, yeah, is what we actually want to be doing. We don't want any of this stuff. So we're just going to be basically spamming it with the transfer PPS, right? And so we know the light probe P. We know the transfer photons per second that we want in there. We know the light solution. And what else do we need? Light position, light color, spam position. Oh, so okay. That's for our fall off. So again, this is where we kind of have to figure out information we don't actually have, right? And this is why I say this is going to be pretty confusing. But that's okay. So for right now, yeah, I'm trying to think of how we would do this. So you can see here why I'm saying this is going to be the hardest part of the problem. So we want to be able to set our voxels to have nice fall off. And so we want the fall off to be computed based on like where the light was coming from. And so they get a nice sort of lighting, continuous lighting sort of thing happening from there, right? And so what that means is we need to produce information about that we don't actually have, right? Because we're getting light from everywhere, not just from certain lights. And so I feel like that's the tricky part, and we're going to have to like actually have some kind of a lighting position information coming in. So I think we're going to literally need this stuff here. Like we're going to need the like light C and the light P to actually come into the system. And it's going to be worse than that. It's going to actually be like a yeah, it's going to actually be worse than that, but we'll see that in a second. We're going to actually need like some kind of a structure that tracks these. But I'm starting to sort of get it now. I sort of get what's going to happen, so that's probably okay. All right, so moving on, what's wrong with our spam voxel here? Let me just get that one correct. Oops. I just want to clean this up in kind of reverse order. So the transfer PPS right needs to be added. The light C is not actually there. So looking at this code, it's that. And so in here, where we actually compute the transfer PPS, it's like, you know, something like this. So if we actually average like the location that the light is coming from and the amount that's coming in, we could actually use the amount to weight the direction as well. You know what I mean? So in other words, like we could say, well, what's the total like what's the total amount of power that's in this thing, right? You know, like maybe something like this. Something like that, where we get the total amount. Can we do this? Do we have RGB in our Vec3, by the way? We do. So if we look at our red, green, and blue and say, look, the total amount of stuff that's going through here, that maybe is our weighting. So we say, like, look, sum the lighting that we're getting incoming, but weight the directions, right? So the light, or weight the locations that it's coming from, right? So then we would say, all right, you know, this light position is now some kind of a weight here, and we're going to want to sum that. So like, you know, maybe this is like actually this power, and like total power, you know, plus equals this power. So we know how much it is, and we can invert it, right? So like power m equals 0, or power coefficient, something like that. If this power is greater than 0, then the power coefficient is 1 over, right? We just basically want to do that. We have a utility function for it. It's called safe ratio 0. And so what we can do is just say, look, let's take the safe ratio 0 of the total power. Sorry, I don't know why I said this power, I meant total power. Take the safe ratio 0 of 1 over the total power, and that's going to be the coefficient that normalizes our position to a location, right? And so we could average the positions of the light that were coming in, weighted by how much light we see coming in from there, and we could use that, right? Now that's actually not a bad averaging rule. I'm like thinking in my head, I'm like, oh, that seems pretty reasonable. But again, the only thing that's not good about it is it doesn't tell us what to do when we want to start making this higher fidelity. Because remember, if we only had one light field, so if we were only providing a single light field, then okay. Right? Then it makes sense. Because basically what we're saying is, look, this is the best we can do to approximate an incoming light position and an incoming light amount. And then we can basically just say, okay, spam the voxel with that information that we've received. However, in this particular case, we know that we could store a lot more information in the voxel. We could store multiple incoming light directions at every voxel position. And the question is, what would we then do? So if we knew we could store more than one, we would need to do something here that allowed us to take whatever information was currently in the voxel and say, well, or I mean, not necessarily what information is in the voxel, but like of the rays that we cast, when we have information about lighting directions, we would need to be able to split the lighting directions up into like at least 4 separate pieces of information for the lighting directions that we would then use, right? And how we keep track of those 4 is pretty confusing. Yeah, so that's confusing. We could do something like having the sphere information tell us that. We could keep a list of the highest power things we saw. Gosh, I just really don't know. I just really don't know how we're going to do that. I think there's a lot of different ways we could try it, but none of them in my head seems like an obviously right choice, so I just don't know. Anyway, what I do know is that our light information here, yeah, it's going to have to look something like this. We need the total power to be summed like so for each light index there, and then we're going to need some way of doing this stuff here. So light sample and sample ref color here. Light sample is not a thing that we actually have. I'm not sure where that came from. It's probably was in here. So we probably need this light C to actually be called light sample, and then that'll flow through properly in here. So I think that's all we really need. And then we should be okay, except for the fact that we haven't actually written this function yet. And then we've got this light position here, right, which is probe sample P declared. That's actually true. So we do need the probe sample P in this case to be sort of consistent. So if we have the light coming from the moon, we need that to be set. So we kind of need this to basically look more like this, like the probe sample P needs to be set outside, and it needs to be set from the moon location, like wherever that's going to be. And we don't actually know, I guess, where that's going to be, but like we need there to be like a moon P, right? And so where we actually set up the moonlight, we need, you know, something here that's like, where did you think the moon actually was, right? And we don't know, but it's probably like way the heck up there, right? And in order for the fall off to work properly, the spam voxel is going to have more information in it as well. So for example, if you look at what's going on here, this fall off equation is not going to be correct. Like the moon's not going to have a fall off. It's just going to be ubiquitous, right? So we would need this to also be something that gets passed in there. So for example, like this coefficient would have to be passed as part of the lighting information. So for example, like light fall off, that would have to come in here, right? And the light fall off of 0.05f or whatever would have to be something that was just set as a separate thing. So, you know, who knows what we're going to set here? I don't really know, but like let's say we set the light fall off to that in this case, and we set the light fall off to 0 in the other case, or something like that, right? And so the fall off factor would also have to be averaged, right, across these runs. So we'd have like this light fall off, and it would get summed. Again, just doing a simple summation here, not particularly clever or anything. Oops. And that's just producing the rolling average of how these things should be falling off with distance. And those are things that we can set again in the probes, I mean in the lights when we push them on if we want to. Again, it's just like some light parameterization stuff we're going to have to decide as we start to tune the lighting. It's arbitrary, and we can do whatever we want there. We can even have other kinds of equations if we need to. It's pretty flexible, and that's not, like it's just a little computation here that's not too expensive. So what we like to do here under the power summation stuff, same exact way we were doing it before, is we need to take that fall off and just normalize it out, like so. And you know, maybe we do these in 2 steps that we can actually see. So like light P, you know, times equals power C, light fall off times equals power C. That way we can see what they are before they get passed when we're debugging. Again, not going to do anything different in terms of the actual code generated, but it's just something we can kind of inspect a little easier. And that will give us all the information that we need now, and we just kind of now need, oh, and we need this fall off to actually be specified here somewhere, right? Okay. So now that's all good, and in here we need this to be passed as well. So the light fall off comes in here, and the you know, this is a really cumbersome thing to do, but I'm just basically, oops, adding this one parameter. And again, we don't really know that this is the way we're going to want to do this, but you know, we're just trying to get things working in a way that makes sense and produces reasonable results, and then we can worry about the speed of things sort of as a second pass down. All right, so we need the light fall off to be passed here, and in this case we know that it's just always 0.05 because that particular routine is the test case, which just is always going to have the same fall off specified for it. It looks like this is a little unhappy right now. I'm not sure why. What did I forget to pass? We have the lighting solution. We have the spamming location. Oh, well, it's not spam P, it's cast P, so I suppose that's probably the issue there. We have the lighting color, the fall off is correct, and then the test case passing down, so that's all good. In here, we know that the irradiance stuff is gone, so we just need to delete it, and that should be fine. And I guess that's it. Yeah. So now the only thing we really need is a way to produce light samples, and then we would actually be done, quote unquote, although, like I said, the hard part is still coming up. So what we need to do here is just have a way of sampling the lighting instead of in the shader, in the actual outside code, right? So we need a way to sample this in here. And so let's go ahead and get started on how we're going to sort of do that, although actually at the moment I might just return nothing and focus on a sort of a separate part of this problem. So maybe I'll call this sample in. So maybe we won't actually implement this quite yet because I might not really care about that part yet. We'll see in a second. Let me take a look here. What is the problem here? That is the problem. This was supposed to be transfer, and it wasn't. So that's just a hasty sketch of how this routine might look, but what I'd like to do is fall back to our test case first, because I think there's some things now we can do in the test case, having looked at that, that will help us out. So the first thing we can do is put the lighting into the actual raycast. And like I said, that's going to have to happen because we currently have the test cast hard-coded to just use a hard-coded light position, but we now want the lights to actually be coming from the environment and having as many as we want. And so in order to do that, let's start actually putting those lights into the casting hierarchy correctly. Right, so that's something that we want to be able to do now. So when we push a light in here, we want to actually push those lights using the push light call and pick them up out of the system using the push light call. And so the way that we want to do that is, inside we may want to put them in a separate array. It's hard to really say. I'm guessing that we probably do, so that we would have a split where we would have, occluders and lights would sort of be treated a little bit separately. And the reason for that, again, is because we probably want to sort of bias ourselves to shoot towards light sources sometimes when maybe we wouldn't ordinarily have done so. And there's different ways we can do that. And, I'll be honest, I'm kind of interested in thinking about that a little bit. One of the things we could do that is not something I really am super familiar with, I haven't heard of it being done before, but I'm sure someone's done it, is we could actually raycast and then bend rays towards light sources as a separate thing, based on sort of the spatial hierarchy culling a little bit. This is sort of a strange idea, but let me draw it out for you just to give you some perspective on what I'm thinking, because it's kind of a weird idea, but I suspect it's not weird enough that I don't think someone's probably tried it before. I feel like someone probably has tried this before. Maybe it's stupid, but I feel like it's not entirely ridiculous. Why is my cord is all messed up here? Use the drawing tablet. Enough. All right. So So if we take a look at how this is, working, essentially what we're going to have is we've got a spatial partition, and we know, I guess I should say spatial partitioning of lights. And I'm not sure exactly how we want to look at this, but effectively what we want is, we know that lights are maybe somewhat rare throughout our scene, unfortunately, meaning that, the chances that you'll hit a light source when you randomly cast a ray might be kind of low because, in certain scenes there may only be 4 or 5 lights. Maybe in some scenes there's hundreds of lights, and you'll definitely hit one if you just randomly pick directions. You'll hit one pretty quickly. But there may be other ones where the entire light is just coming from one candle or something, or torch that the hero is holding or something like that. And in that case, most of our rays will miss. And so we won't be able to pick up that light sources as much as we should, right? And so if we want to bias towards making sure that we at least sample the place where the light is actually coming from, what we need to be able to do is know that for a given location where we might bias towards. And if there's only one light in the entire system, that's fine. But if there's 10 lights in the system, but 1 in each room, then the lights that we cast from a particular room want to bias towards the light in that room, and so on, right? And so all I was saying was, if you imagine how the spatial partition looks, you've got something like this. If we imagine top down, and maybe we're casting rays from here, right? And there's light sources maybe like here, 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 and here, right? And all of these are maybe spatially partitioned. Maybe this room, right, has solid walls, so you're never going to hit these, right? And so what we'd like to know is, if we're casting rays from this location, when we want to bias our rays, we want to bias them towards this light source, but we don't know that, right? So what we would like to do is perhaps make use of our spatial partition to say, hey, what are the lights that are nearby, and maybe only bias towards like these two, but don't bias towards like this one, for example, because the chances that you're going to hit that one are actually pretty low. Know what I mean? So what we'd like to do is have a way of bending rays towards light sources based on the spatial partition. And what I was thinking we could sort of do is something like, well, what if we just look up in the spatial partition? What if our spatial partition stores like the closest light source at each level of the hierarchy or something like that? Or like some kind of a way of producing that information? I'm not sure exactly what I mean, but like imagine that as we build our hierarchy of bounding boxes, at each level of the bounding box, we store what the light source is that is most central to this one. And then as we find probe locations, we expand down to the point where we look upward from where we are until we gather some fixed number of light sources that we bend towards. Does that make sense? Do you know what I'm saying? In other words, imagine for each light probe, we look at where the light probe is in the voxel, and we walk upwards from the voxel. Not voxel, spatial partition. We walk upwards through our parents until we get to 4 light sources, and then we go gather what they are. Is that stupid? That could be pretty dumb. So I guess what I would say is it's not dumb enough that I don't think we should try it. But you get kind of what I'm saying, right? So in other words, we would just find a node that the first node that contains 4 light sources. And why 4? Because that's how many we cast in a packet. We would do 8 if we, if we were doing something else. If we were doing AVX2. So we just, however many we cast in a bundle, we'd look up that many. But I guess what I'm saying here is like, so if you imagine in our lighting work here, do we even use these? I don't think we use these anymore either. All right, so we'll probably, we can get rid of a lot of code here eventually. So if we assume that we've got our lighting is kind of packed into this array of boxes, right? So you have this lighting box set here. And if we look at the lighting boxes, right, our spatial partition is like built out of these things, and these are, these are sort of the things that we push on for occluders, and also what we could push on for light sources. And all I was really suggesting is, well, if we actually said, maybe instead of like emission, right here, we would basically just out-reference. We would basically say like things that have actual light sources associated with them can like reference those as a separate thing. And then when we sort of go up the hierarchy, maybe we say, look, we just store in here, instead of an F32 for emission and a texture index, like maybe like forget that. We've got the, P, the radius, and the ref C. What if we just said like, all right, there's, a U32 of like 4 lights, right? And as you sort of build the spatial hierarchy, you propagate the lights upwards so you know how many lights you have. And so what we would do is we'd walk up the hierarchy till we get to something that actually has all 4 lights, right? And you can imagine doing this in sort of a squinkier way. If you limited the number of lights to 65,000, which seems pretty reasonable, you can imagine saying something like this, where you just said, like, look, there's a U64 that says what the lights are. And what we do is we pack 16-bit indices, 4 of them in there. So as you come up, you can just say, look, if any part of this thing is all zeros, which would be a pretty easy thing for us to test. I guess I don't know why we couldn't just do that as well. Just test to see whether any of those are 0. And if they are, then we know we have to keep walking up the hierarchy further to try and gather more lights to bias towards, right? Just an example. We could go one further, and if these lighting boxes were even spammier, we could do something else where we just said, look, we keep which 4 directions we have. In fact, so we could do something like this, where we basically say, like, hey, yeah, there's like a something like this. So we just say, look, we take these lighting boxes, we pre-compute the bias directions towards light sources, and we store them into the hierarchy. And that way, you just look up in the hierarchy where you are, and you immediately know where your bias directions are. So we just do that as part of the box building pass. One pass through the hierarchy to just build those, right? And then every point that actually looks up in the hierarchy just knows by pulling that out. And the only reason I put that in there, you know, and it would look like this, right? And this can be a U16 as well, so it would really probably be more like this. So the lighting boxes would just have this information as a primary component, and then in here that would actually just it would just store the sort of an out-of-band light bias lookup, right? And then inside the lighting solution itself, we would just have as many of those as we wanted, like a buffer full of lighting bias directions. Because we only need as many as there actually are containers of 4 light sources, pretty much. So I don't actually know. The only thing I'm not sure about is what do you do sort of on higher up pieces of the hierarchy, but I guess you don't care. Once you have 4, you don't need anything above that. No one would go above it anyway, so I think you don't care. In fact, this only really needs to be stored at the leaves, I would say. So you really can only have as many as you had leaves in the first place, and you don't need even close to that many because the lighting directions will not vary per leaf. So, but point being, you kind of know, I don't know, we can get rid of a lot of this stuff, but we know that, like, you know, if this box table here that we have, we know at the very least that even though it's quite piggy, we could introduce a thing here that was just like, look, we've got a crap ton of these things. And we could even get rid of this if we had the thing be that big, because you could actually just store it. You wouldn't have to push them on. You could literally just know that you look up your index and you'd get it, right? So this kind of gets simpler and simpler as we go. Yeah. And really all you have to know is that the number of occluders, and I don't know why we still call this light data width, but the number of occluders can't exceed this value. But other than that, you're fine. So all right, so I think we're kind of slowly walking into it here. So if we have the light directions to search in there, then really all we need now is a way to encode whether something is or isn't a light. And so I think that's the only thing that then needs to get looked at a little bit more carefully. And so when we're actually putting these things in here, we need some way of saying that information, like is this a light or isn't this a light? And what we could do here is like the refc, for example, we could just say, all right, maybe we just have like some kind of encoding convention, or maybe we just have a Boolean, right? Like maybe we just have something in here that says. And so if you look at what's going on, this is 9 values here, right? And this is a 10th value. So if you look at like, oops, where's speed calc? There we go. So we've got 3 vector 3s, right? So that's 3 times 3 times 4 bytes. So we've got 36 bytes being used up there. Plus we have two 2-byte fields, which gets us to 40. And so, you know, 64 is a cache line. We want these things to fit in a cache line. We're in no danger of like falling out of it. We could try to make it a little bit more compact, but I don't know to what extent we could really do that effectively. We could certainly just keep it at 40. We wouldn't have to grow it if we didn't want to, because although this would have to be U16, this certainly doesn't have to be U16. So we could probably easily say that the child count is, you know, we don't ever split into that many. So we could also say like that, and that would be fine, right? So we could sort of start chopping it down to that. And then the refc, instead of being a reflection color, is actually just a thing that tells you whether this thing is a light or not. The color of the light, right? So if the is light is on, this thing is the color of the light. If the is light is off, then it's the amount of reflection that's going on, right? And that'd be it. So here when you push occluder, obviously like is light is set to 0, like so. And then when you're pushing a light source on, is light should be set to true. Since this one's a U8, actually I guess these two are both U8s, so those should be separated. When you're pushing a light source on, we just need to do sort of the other thing here where we would, you know, where are we actually pushing that on? I don't actually know. So here's the push cube call, but we don't actually want to push a cube when we push a light. So that's not really actually what we want. Let me go to the push cube call and let's take a look at where that actually was there. So this is what we want. So push occluder and push light are actually the same pretty much. So I'm gonna put those up. It's not push cube at all. So it's really this. So what we actually want is this right here, this code exactly, and because we don't want to do any of this. This is just wrong. So what we want to do is when we do push light, we want to have this be the emission, right? It's RGB emission. It could be whatever you want. And so in here we would encode that information. Here's the P, here's the radius, and here's the emission, right? And then this right here, we would want to set these two to 0, but now we're setting this one to true, right? Or to 1, effectively, right? And we don't want textures here, so we just really want that. Like that's pretty much all we want. And when you push a light on, that's what it should look like. And so in here, let's see the hit emission stuff. So we will work with that in a second. That's what we want to be working towards. Let me just figure out the rest of the stuff here. So source count. When we do split box here, what does source count actually do in this case? Do we actually need to use 16 here? Like, why is this? What's this doing? The source count and the source. Does the source get reduced here, or what happens? Source count 2. I think that's all we actually want to do. Wait, that's not going to work. So wait, how did this thing work? Why? So it actually needed the U16 even though you can't actually keep that many children? I don't understand. Oh, wait, no. So never mind. This just does the split box, and either it comes up with 2, or it comes up with some number probably pretty low. So I think I can do what I was going to do, which is just keep those like this. And so here I'm going to just assert that we didn't lose any information there, and go from there. And so here with hit emission, that's the part we want to work on in a second. What's this part here? Oh, so for push light. So in this case, we just want to do like whatever the emission was. We would multiply it. Now we don't really have to do that, right? So we could actually just say like to do KC probably can just use RGB for emission and encode that directly when we create the entity, right? So that part should probably just be something we can change in the future. We don't need to do that kind of little dance there, but all right. So for now, when we do the hit emission here, right, we don't actually want to store hit emission because the ref color actually would tell us what we need to know there. So we don't have like an emission scalar. So what we actually would have here, right, is we just need to know, is this thing a light source? So it's effectively just selecting like a Boolean value for like whether the thing is a light or whether it isn't a light, right? Because that's what we need to know on the outside. And because, well, is that actually true? What do we do with hit ref color? Yeah, I mean, I guess it is true. So we just need to know that fact, right? And so I guess we just want to store that as a mask. I'm going to guess. I'm just going to go with yes. So when we actually do the raycast result here, like instead of emission being I mean, basically it's going to be a Boolean, right? This emission, like it's going to be is emission, right? And so in here we would have like this selection is still correct in a sense, but this emission value that we're loading up here is actually going to be like is light, right? And so what we want to do there is say, look, we've got an all ones vector and an all zeros vector, I think, right? Do we have 0? I don't know if we actually have 0. So I'm not sure if we actually have a thing that would do this. But what we want to do here is for the box, right? We are loading up the information for this one box, and it either is a light or it isn't a light, right? So what we need to do here is when we actually hit it and we get the hit emission value, and here we're going to be setting that value like this. So this is emission is going to equal the hit emission. What we need to know here is basically just a 1 or a 0 that goes in. And so, you know, it can basically be like an emission coefficient. So, I mean, it really still is the emission value in a sense. I mean, we could actually even just keep calling it that. But it's just going to be a 1 or a 0. It's right, whether or not you're going to have that or not. And so if the is light is set, we want to load a 1 in there, right? So it's kind of like this. It's like that, right? And I guess this is already specified. So we want something like this, where we just conditionally load one based on which one it's going to be. And so it kind of makes me think the box wants to have that as an F32. I mean, it's... All right, so I maybe kind of take it back. I feel like we kind of want to load that as an F32, maybe, right? So in here we would say like is light is actually like an F32. So it either gets set. I mean, it's wasteful. I don't love it. But you really don't want to be like Boolean all over the place. Yeah. So I take it back. So I guess we're going to do it that way. I realize it's not the best thing in the world, but I want to be able to like load the thing fairly directly from there. And maybe this is dumb because, hey, you could have just used a conditional move into a register and then load the register. So maybe that's dumb. Yeah, maybe it is dumb. I'm so torn right now. You can see how I'm vacillating here. But I guess we could just do this with a conditional move. So it's not that big of a deal, right? But basically in here we could say, all right, look, we need to first figure out what the F32 is, which is like is emission. And is emission is just going to be a conditional move that's like, look, is the thing a light? If it is, it's 1.0. If it's not, it's 0, right? Or something like that. And then we can just load that thing in via the standard load. I don't actually know. We'd have to look at what code this generates, but this could be bad. That's all the reason I'm saying it. So I don't really know. We want something that's going to generate efficient code for that loading, and I don't really know what it's going to be. Let me look at the F324X here. So that's what I actually wanted. So I just don't really know what I want to do there, but something that does the equivalent of that, which is gets 1 in there or 0 in there. And then that way, on the way out, we know what is and isn't lights based on this. And then that way, in the outside, right, where we get this emission back, it's just a multiply, which is what we want. Like, we don't want to be doing like if statements in here. We just want to be doing straight ahead computation. So we really want like a 1 or a 0 that like turns that on or off, right? And we may want to do something that like does a 1 minus for this, because we may want to not sample in the case of a light. We may not want to do the light transfer here. That may just be wrong. And so in a sense, we may want to say like, oh, okay, yeah, this, and also this ref fall off part, right? I think what we want to do is just roll the emission into that, right? So we want to say, look, whatever the emission was, if it was set to 1, so it's going to be a light, we want to, do this instead. If it's, in fact, and you know what, we could actually do this a little bit differently even. We could just say like, yeah, the ref fall off is the, no, all right, never mind. It is the way it should be. We're going to say, look, if this emission was set to 0, then we're going to use the ref fall off times the Hadamard here. This term will come into play, and it will do whatever the reflected light is. Whereas if emission was 1, then you hit a light source, so we're going to provide just what the light source color was, right? So it's basically like a toggle. That emission is just a toggle that says which of the side of the equation we use, and that's how I think I want it, right? All right, so I think that's roughly what I want to have happen there, and we can sort of get a little bit further down that rat hole in a second. But for right now, what I want to do is focus on the test code here and really work on the test code before we start to try and use the propagation version. And the reason I want to do that is, first of all, this is just using the debug light P. What I'd like to do now is switch to using that as a push call. And let's get that working properly as our first thing we do, right? Okay, so in world mode, where are we looking? We have the debug light P, or whatever it is, right? See that here. In this call to push light, you can see that's actually what we want. So we want this push light call here to come back into existence, right? And what we want is for this thing now to work with our system correctly. So this is the light that we're pushing into the system. This is the location that we're pushing it in, and the radius, right? So now we actually have a push light that's pushing into the system, and it's putting an occluder in there that we should be able to actually, like, the occluder now would actually exist. I don't think we're drawing it at all, but, well, you can see it, right? You can see that it's occluding the light source, right? Because it's there and it's blocking it. And when the hero hops up so that it hits the light source, right, it's actually putting the light into it, right, and so on. So we're in good shape there, like we know that that's actually being pushed in. And what we want to do now is say, like, okay, that's not an occluder, right? We know it's a light because it's got the lighting thing set. It's not an occluder, it's a light source. Now we need to actually, like, track that information. Okay, so in the test cast from probes part of things, right, I'm still going to cheat and use the debug light position to know that's what we're casting towards, but instead of doing any of this stuff now, we're going to do this a little bit differently. So before, what we were doing is say, look, the hit is whether or not we got to the light source before intersecting something, but now what I want to say is, okay, we don't know. We just know that we did a cast that hit something, and so now what we want to do is say, is that something a light source, right? So now what we would do is say, well, hit, for example, what we could do is just use, all right, is that emission value 1 or 0, right? So for example, I can just do that, right? So now we're just saying, look, is the thing we hit an emitter or isn't it, right? And now we would not actually be testing anywhere else. Also, I want to get rid of this secondary bounce thing because we're not going to use that. It was something that someone asked us to add in as a test. We don't want that in there. So anyway, now we're saying, look, we're not going to cheat and just say, did we hit the light source or not? What we're going to do is expect the raycaster to tell us if we hit a light source or not. And now let's debug that, right? And so now what we need to do is go figure out, you can see it's like totally not working right? You can see it's like all kind of weird now. So what we want to do is now get this working. So we need to figure out a way to make it this work correctly for the debug light. And this will give me an opportunity to debug having lights in that hierarchy, which is exactly what we want, right? So when I actually hit something, we need this emission value to be coming out correctly. I just want to make sure I wrote this code properly. That does look correct, doesn't it? Sort of, maybe. I think so. I think so. I'm going to turn on the line drawing as well. And in this case, I want to, the line color should be based on the hit, does it? Yeah, it is based on the hit. And so what I want to do here is make it so that it's clear whether we're hitting the light source or not. What I want to do is make it so that if we hit something, this is backwards. So I'm gonna change this to hit light. I'm gonna reverse the meaning. So if we hit a light source, that was here. So if we hit the light, we will say hit light gives us a yellow, otherwise we get a black. If we hit the light source, well, this is now hit P is always correct, so that's good. Well, no, if we didn't hit anything, it's not correct. So if we have a cast that's like just too far, right? So if we have a cast that just went on forever, we wouldn't necessarily have a way to draw it. So what we would need to do here is say, well, if the cast T hit equals F32 max, then what we would need to do is say, you know, we didn't hit anything, but that shouldn't be possible. You know what? I'm just going to get rid of that case for now. because we're aiming at the light, so we're either going to hit the light or something else, right? So if we don't hit anything, that should be a bug. In fact, this right here is just a bug, so I guess this should this is what this should do. This case should be like something very bad happened, right? This is an error, right? And so then in here, if we hit the light, then we spam the voxel, otherwise we don't, and I think that's all we really needed. What is it actually? T-ray, sorry. So that is something now I can debug and look at, right? So now I can look at what's actually happening there. I probably should turn lighting off so I can actually see it. Although actually it looks like it's working now that I've kind of recoded it properly to talk a little bit more correctly about what it's doing. I think we just had some typos in the code there. So I think that just worked, actually. We don't really need to debug it. All right, so the light is now coming from the actual voxel. And we should be able to have multiple lights with multiple shadows now also by spamming a different part of the voxel, right? Like we could interpolate multiple light sources here as well. But anyway, that just shows that the test case is working okay and that the emission stuff is working okay. And we know the difference between an emitter and an occluder now, right? Which is what we wanted. So I think that's all good. And now if I were to take out, so this now becomes sort of the next thing we might want to try. Now let's try tracking the light so we don't actually have to ever set the debug light. We can just pick it up from what's in the voxel, right? So we know that's working. What we don't know is this value here, right? So what we want to do is discover that. We want to discover that from the voxel. I mean, why do I keep saying voxel? We want to discover that from the spatial hierarchy. So in terms of which light source I would want to bias towards in the spatial hierarchy here, what I need to know, looking at the lighting, is I need to be able to sort of crawl down that spatial hierarchy, that partition, and I need to be able to get down to my leaf node and figure out what the light is in that leaf node. And so I guess I'm not sure. I think the way we were doing this here, you can kind of see all it does is it basically just like uses this box stack to see which ones as it kind of goes down. So I'm pretty sure we can kind of just gank this routine and find our closest one really simply. So let's just kind of grab this guy. This is not really that necessary, but like I don't really need to copy hardly any of this. But so if we wanted to say like get leaf for P, or spatial leaf for P, and we pass in a position, right? What I want to do here is say, well, we probably don't really need a box stack for this because we can only be in any one box at a time. So we would just open up a children, look at which one, pick one, go down it, right? We don't have to ever actually use both sides because a raycast needs to consider both sides, because if it doesn't hit something in one side, it has to go to the other side of the spatial partition. In our case, we're just going down one at a time. So what we can really do here is say, look, there's just one box. We don't need a stack. So we can basically just say, that. So we start at the root box, and then all we're really doing is saying, let's traverse down. What we want to do is go through the children of this box and see which one we're in, right? So we just need a way of determining whether we're inside this box. And then executing this code, I believe. Probably also want this. Right? So what we would do is say, all right, here's the position. We start at the root. We go in and we see for each child that we have here, we want to pick out a new box that's the one we're in. So we would get the box here, and we would say, like, if inside, right, and off we go, like that kind of thing, right? Now, what we do want to do is we want, I guess, to accept also a case where there isn't one, I suppose. So, because if we ask for something outside the hierarchy, you would get nothing, I would assume. So here we would probably do like, we start with the results children, I guess. I'm trying to think of how we avoid infinitely looping here. Like if we loop over everything and haven't found one that we're inside, then we have failed, right? So we maybe do this. Perhaps. So essentially what we want to do here is say, okay, start at the first child index, one past the last child index, we loop over all of these, we look to see whether we're inside this box, right? Assuming we are inside the box, if the child count is valid, then we need to descend, so we just get out of the loop, right? And we set result equal to the box in question. Otherwise, we actually just return the box directly, right? Something like this. This doesn't look great. Something like that. I'm not sure that's very good. Let's think about this a little bit more. There's probably a cleaner way to write that. You can see what I'm trying to do here though, right? If we need to keep going, we keep going. If we don't need to keep going, we just leave. I guess this is the only return point, so we could actually just also say this, in a sense, because everything else is a failure. I don't know. I don't think too hard about that at the moment, but this is basically what we're looking for, right? So if we did a get spatial leaf for P, we need an inside box, like an is inside kind of a thing here for these boxes. And I guess I don't know, like the lighting box here is a P and a radius. So basically what we need to do is figure out, like, are we inside this thing? And so that's pretty easy for us to do. We already have an is in rectangle, right? So we can also, we can already do this. And we just need to construct a box here, and that's pretty easy for us to do as well, because this is it, right? So it's just that. So I think that's all we would actually need to do there. It's not as efficient as probably we would like, but I think that's it. And then this we just need to pass the position to, the position to. And I think that would get us whichever spatial partition we're actually in at the time, right? So that just returns the leaf to us, and we're good to go. So that means that if we wanted to take the test case, right, to do the test cast from probes, and we didn't want to cheat and use this debug light P thing here, what we could do instead is say, look, get us whatever the leaf we're in, like so. Don't know why this is this when it should be that. So we just say, look, get us the leaf, and then we'll get like the location of the light from the leaf, right? So the place that the place where the lights are supposedly at. For this leaf that we're tracking, let's get those, right? And so what I can do is say, if we are actually start tracking those, right, and we go into the lighting code here, and we look at how I was proposing we store those, right, this right here would be the light box, actually the light box target P or something like that. So this would be the target positions for the lighting, or the places to try to aim towards. And there'd be 4 of them for every, there'd be 4 of those for every one of the leaves that we would store. And we would look it up using just whichever leaf we were actually in, right? So we could get the box index. And in fact, I guess the box index is sort of what we want to return for the leaf itself. We don't actually need this information, so I guess it's more like this, right? And then what we would do is say, okay, the light P that we're actually interested in is just the solution target P for that leaf index, right? I think you have to do a get component on that. Yeah. That's right, isn't it? I think that's right. And so that would be a way that if we were actually building it, we could get them out pretty trivially. And what we need now is to get that actual leaf location. What did I actually call that function? Spatial leaf for P. So now what we would do is say, well, the results, I guess so in this case, right? I guess this is starting to look a little bit more sane here. So we could just say, look, we assume the result is 0. While we don't have a result, we would go to the parent here and we'd say, like this. Parent first child index, parent, oops. First child index plus parent child count. So that gives us our range. We assume that there is no more parent. So we could also say while parent and not result, like so. Parent equals box. So in either case here, if we're inside, we break. And the difference is just which one of these two we do, right? So it's a little bit of a nasty loop. It's not the world's best loop in the world, but it sort of works a little bit maybe. So I think that gives us the cases that we need, and off we go. So now, get spatial leaf for P. P is undeclared. That is true. We need the light probe position. So here's the cast P. That's what we're actually looking for here. And now we can sort of comment that out and get the light position directly from our spatial hierarchy. And that's what I actually want to do here. We only have a few minutes left, but let's try to actually put that information in now. I mean, why not? So how are we going to do that? We've got this sort of box splitting nonsense going on. So how are we going to figure out where the lights are and all that garbage, right? So let's take a look at how that code is working currently and see if we can reverse engineer something, or sorry, reverse inject. I don't know what you want to call it. Something in here does it. Because right now, if we did this, it wouldn't work, right? Right now, if we did this, we'd get nothing because this stuff is just going to be 0. And so the location of the light source is going to be 0, right? There will be a light. It'll just be at 0, 0, 0 or something weird like that. And the shadow will be computed from there, but the other part won't be, I guess. Is that right? Let me see what's actually going to go on. I don't know exactly what's going to happen there. So I don't know. So I guess if I'm honest, I'm not sure why we were seeing the light move. I'm kind of weirded out by that. I guess that's because well, you know, I don't really know why that's because. I guess it depends on whether you hit the light in there. That seems buggy to me. I'm gonna go ahead and finish what we were doing, but I think there's just a bug in there. I don't know why we're seeing what we're seeing here. That doesn't make much sense at all. I don't love that. All right, so anyway, I'm gonna go look at the split box, how this stuff works. So you can see our build spatial partition for lighting call. What this is gonna do is it's running through all of the boxes here. It takes the total bounds, right? So this is basically like how much space am I actually taking up for the entire set of occluders. It then goes and says, all right, let's go ahead and start splitting these boxes, right? So it takes however many boxes I guess we actually have total. And it says split them up, right? So I guess in here what it says is when we go to do a split box call, assuming that there's more than 4 boxes, because we're going to store 4 boxes per leaf, I guess, we go through some attempts and we look to see like how to divide them up, I guess, with some rectangles. Assuming that we find some way of categorizing them cleanly, we go ahead and do the split box, and then we go through, right? And so I think all I really need to do there is pass up information on the lighting, right? So in this case, if the source count is greater than 4, we try to split. If the source count is less than 4, then we know that the things inside us, we want to look to see if there's any lights, right? So what we want to do is say, look, are any of these things that we actually have in terms of our children here, which I guess is this? Yeah. Here's our children. So I'm not sure. So we're moving that pointer around too. Okay, this is a weird way to do this, but all right. So what we're doing here is we're saying, look, for each of our child boxes, is any of these a light, right? So it would be this. And if it is, we want to put it into like our light tracking, if you will. And so assuming that we found the light here, what we need to do is propagate that information to all of the nodes, right? So we need to like know which lights are closest for any particular situation. And it's hard to say. I'm not really sure exactly how we want to do that. It'd be pretty trivial for us to just store any 4 lights that are in the vicinity. But it's considerably more difficult for us. We would have to do something more clever if we wanted to actually get the closest light each time. So maybe we want to actually insert these lights, which seems costly. And I'm not really sure I want to do it. Because it'd be ON in the number of lights, which I don't want. So probably the better thing, it'd be ON log N in the number of lights, which seems bad. And I think we probably just want it to be the initial ON build, the ON log N build. We don't want another N log N pass. Or maybe we do. I'm not sure. So let's do this. Let's just say, look, if there's a light in here, I'm just trying to think of, well, but we can't really do it as a inline here because we need to back propagate it down as well. So All right, so I don't really know how to do this without doing it as a second pass that will actually work cleanly. So really hard to say. But it seems like what we would have to do here is actually have the lights, in this case, be sort of handled as a separate pass, right? So after you split them, you would go through like this, and you would say, you know, if this is a light, then you need to like insert the light. And when you do the insert light, it would flood through each of the levels of the spatial partition, right? And figure out if it was close, further, or figure out if it was better than the lights that currently were in there. You know what I mean? And so thinking through how that's going to work, it's pretty nasty. The first light that gets inserted would be the closest light at all points in the hierarchy, so you would touch all the boxes. The next one would be, you know, like half or something, depending on where the lights were. And you would touch less and less, presumably if you had a way of guaranteeing that you couldn't be the closer light, but this just seems terrible. So I don't know how we should find that piece of information. I mean, another thing we could do is write them into the voxel. So basically, like, we're just storing the closest lights in the voxel, and you aim for those. But again, even there, you're talking about it's kind of a hard thing to know. I'm not sure. I think since we're out of time, what I'd like to do is table this for tomorrow. And relook at it then. Because I feel like I want to think about this some more. And there's a lot of things we could do here. And I feel like we need to kind of draw them out and go, okay, which one of these is the most likely thing? Again, we could just not do this at first, right? We could just use stochastic sampling and just like see, you know, if we hit the light source, we hit the light source, and if we don't, we don't. And that would work fine. It's just not as good, right? So our lighting is going to be more flickery, and less, you know, likely to pick up the lighting features than if we do some sort of biasing towards lights occasionally. So it seems like something we do want to do, but how to actually quickly determine which light sources to bias towards is sort of something that it doesn't seem exactly like there's an obvious way to put it into the spatial partition nicely in a way that's pretty cheap to do. Like the query for 4 closest lights is a little tricky, and there's just a lot of ways we could do it, and I just don't have a solid idea of which one. So I'm going to go ahead and not do that. And so we're just going to leave it as it is right now, and we'll pick it up later. What I could do here is cheat again and say, look, we know we're getting the debug light in here. So what I'll do is I'll just put that in here just to make sure this code is working, because we could get that code working properly. So ignore this, right? And instead, we're just going to do this. So we're gonna like loft that thing up, right, into each of these. So for every box, wherever you would have looked it up, you're gonna get the target. That's the debug light. So we're just spamming the debug light out to all box lookups. And so that way we could just verify that this part was working correctly. And it does seem to. I'm going to turn off those test cast bits there because I don't actually want to see those. And then we're going to go to the Q&A. And we'll think a little harder about how we want to insert those lights in the future. So the test cast here, I'm just going to get rid, oops, I'm just going to get rid of that. And I'm going to leave it like this. So this is now correctly executing the test code. But again, we're not actually doing the lookup. So we're ignoring the look. The lookup will always return the correct thing as it is going there. And so we need to figure out a way to actually make that, that table be filled with correct answers. All right, let's go ahead and do a Q&A. You know what I should do too while we're starting this up? I should see about, is this thing logged into Twitch? I don't even know if it is. If it is, I should see if we need to raid anybody after this. You know what I'm saying too? How do I do that again? I know there's a way to do that. Okay, follow channels. Nope, nobody's streaming. John's been streaming a bunch lately, but he's not streaming now. So I cannot rate him, but just wanted to check and see. You're returning 0 instead of result in the function you created to find the box. Oh, thank you for that. We don't actually use that at the moment, but we do want to do that. So just, we don't want to have to go hunt that down if someone already spotted it, because when we do actually make it work, we would be kind of grumpy about that. So thanks for that catch. Yeah, we'd probably spend some time debugging and go, wait, why isn't it returned? Oh, because it's 0, right? So saves us that, which is good. Not sure how relevant, but the problem seems related to important sampling lights in Monte Carlo ray tracers. Exactly. That is literally what we're doing. This is a Monte Carlo ray tracer, and it is trying to use some direct light sampling to improve the results. The problem is we're not. So the Monte Carlo importance sampling part of things, that part is more about figuring out how to weight the results, Whereas that's not what we're doing here, because we haven't gotten to that stage yet. What we're trying to do is just figure out how do we want to look it up, right? And so Monte Carlo ray tracers also have this problem, but probably a lot of them just use a separate spatial partition for the light lookups. I doubt they use the KD tree for that, although maybe they do, right? I was just curious if we could use the same one. It's hard to say, But what a typical Monte Carlo ray tracer will do is, on every bounce, as it's tracing out a ray, it will randomly pick a number, and if that number comes up, heads or whatever, it'll shoot towards the light instead of the bounce direction. The direction it would have chosen. Because it's already got to pick a stochastic direction in terms of sampling the BSDF or whatever that's doing, And it'll randomly bias towards the light sources or hot regions of the scene. What lessons did you learn from implementing Handmade Heroes debug inspection system? I don't think we really did. I guess what I would say is the only real thing I learned about that was you can't really work on stuff that complicated on stream. It doesn't really work. We would need another 100 hours to get that to a place I think was really good, and probably I would need to be thinking about it more deeply and not talking all the time, right? So I think we could do a good version of it, but I would need to think about it off stream. I don't think really complicated architectural stuff like that works particularly well on stream. That's the only real lesson I learned from it. It just doesn't lend itself well. You need a more concentrated thought time. Any other cues? There's a follow-up question. Okay. I'm waiting for the follow-up. Are there any performance impacts to storing large arrays of data as static global constants? No. There are not. I mean, sometimes you don't want to do that because you want a little bit more control over about when and where those things are created and initialized, right? And when you store large arrays of static globals, then those are going to be done at, load time by the OS loader that's partitioning your memory space, and you can't place them where you want them. You couldn't have a base address with virtual alloc if you wanted. You couldn't put them near or far from something else. You don't really know how they're going to be aligned necessarily unless you use an alignment specifier and blah, 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 right? So, sometimes and also they won't show up on your memory. If your memory allocator tracks things, they won't show up there because they didn't get allocated, quote unquote, by your allocator. They got allocated by the system allocator at startup. So there's reasons why I don't generally do that. I usually, if I'm going to have large sort of arrays that are declared in C, I'll stick them in a struct and then I'll allocate that struct just so it goes through my allocator. And usually, again, that's just because it's nice to not have a huge amount of data segment space just getting created there unless you really need it. So sometimes you'll do it because, in the debug system, for example, you really need it to just be a globally accessible variable or something, then that's fine. But a lot of times I just won't do it that way, not because there's some kind of super bad thing, but just, Jesse Meyer, is a non-trivial part of the difficulty the inherent limitations of C? You originally had to implement various metaprogramming tooling. Or is the ideal system you want just inherently complex? Yeah, I would say it's both of those things. It is both complex and C doesn't do it, C/C++ doesn't do it correctly. So it is both of those. It's both. Both of those things are true. Do you use OpenGL? Unfortunately, yes. I probably wouldn't have done that today, but when we were showing how to interface with a 3D card at the time, OpenGL was probably the best, or I thought was probably the best solution. The reason for that is just because I wanted to have it be as likely as possible that people could follow along on their own operating system. And OpenGL at the time ran on Windows, Mac, and Linux. Subsequent to that, Mac, which I know a lot of people develop on for reasons I'm not quite sure, but they do. OpenGL doesn't really run on there anymore. You can sort of run it, but it's really deprecated and buggy and bad. And Apple specifically said don't ever use it. Right? They're like, don't use OpenGL. We're not supporting it anymore. You have to use Metal. So given that turn of events, I probably would have just used D3D. And certainly if someone's writing a game that's not for educational purposes, I would say definitely don't use OpenGL. I would say use D3D 11 on Windows and use Metal on Mac. And don't bother with Linux because people don't buy games on Linux. And if they do, they can use the Valve translation layer that does D3D translation or something, right? Will you add lights separately or bundled it with other objects in the scene, like lamps, for example? So they're probably going to be a mixture of the two. We will probably have... So right now, entities can specify that they have lighting on them, right? So we will probably do something where some entities, like lamps or other things, are just set to have an emitter on them, and then that'll just happen or something, right? And then in other cases, we may, because again, it's an artistic intent issue, right? So in other cases, we'll probably add lights to the system that are maybe there to help with just coloring in areas in ways that maybe don't really have a reason to be there. There may not actually be a physical thing creating the light. You know what I mean? Because it's a fairly whimsical environment. It's it's cartoony. It's not so, it's not like we're doing something where we really want to push the realism and have it look really like a real scene. So we probably want to put in lights that are not really there sometimes and stuff like that. So not a question, but just want to tell you I lost 2 daughters, twins, due to a freak accident, and binging Handmade Hero helped a lot with managing the loss during the hardest time. You help with more than you probably think. Okay, so not sure how to totally respond to that, because that sounds very horrific. I kind of had this vision in my head of The Shining or something. The two twin daughters with the crazy blood flowing through or something like that. That was very scary. And I guess I would say I'm very glad we could help with that, but I guess that's not me, right? That's just trying to provide... I suppose that's just saying, look, there needs to be something that you can take your mind off of something that horrific. And if we could do that for you, that's great, but hey man, that ain't me. There's nothing I can do about something that bad, right? I guess I'm just providing a good diversion, which is more than fine by me. I mean, if I can help in some small way with something like that, then I'm thumbs up. But yeah, that sounds terrible, I guess is what I would say. I've never had children, so I can't really relate directly, right? But I can imagine that's probably one of the worst things that can happen to you as a person, right? Humans are pretty hard bound to their offspring, right? That's like a pretty primal survival instinct. So there's nothing you can really do about that. Like your emotions are going to be really, really violent in any case. That's that bad. We should have some kind of a distraction stream, like a not thinking about loss stream. We can have Handmade Hero loss diversion programming. Do you think the current trend of dedicated ray tracing hardware is the right way to go for GPUs solving the lighting problem? Is there another route you would like to see? I guess what I would say is I don't necessarily know if having dedicated ray tracing hardware is the way to solve the lighting problem or the right way to solve the lighting problem. But what I would say is we don't know what else to do, right? So I don't know what the right solution to lighting is. You know, as you can see, it's just really difficult to make it work. I think if NVIDIA had a better idea, they would do it. So, I mean, the reason they're doing what they're doing is because we don't know. Like, light gets transmitted along rays. Ray tracing is the only thing we know about that solves the lighting transport problem in a general sense. We don't know what else to do. If someone comes up with something brilliant that turns out to be like way better, we would use it, right? But we don't know. And so I certainly don't have some other route I would suggest because I don't know what else you do. You know, stochastic ray tracing is the only thing we really know how to do. It's the cornerstone of all production renderers for like high-end stuff, you know, that renders movies and whatever. Like nobody does anything else. So it's pretty much all we got. And so it may not be good just because it's so slow. But I don't know what else you do. So just throwing a ton of hardware at it and crossing our fingers is possibly the only real path forward. And the good news is that it's a incredibly parallelizable problem. So, you know, when you think about something like rasterization, there's like order dependencies and things like this. Ray tracing has none of those. So you can literally just throw tons of hardware with no communication whatsoever at a ray tracing problem and it just gets better, right? So the good news about ray tracing and the reason why maybe it could be a right solution in the long run is, look, you can throw 62 chips, each with 300 cores, into a machine and have them all ray trace, and none of them need to talk to each other about anything, right? You've got a problem of how you distribute the scene geometry out to them and how they actually get information about like what textures they're hitting and stuff, and that's a problem, but it's still fully they don't need to talk to each other to do it, right? Like nobody needs to synchronize or like they just need access. So you're just talking about how do you replicate information across a wide network of computing elements. But if you can, you're done. Because if you can get it replicated out to enough things, they will just run in parallel and they never need to talk to each other. And that's a really powerful element of ray tracing that it has that not many other things do, right? So that's the really nice aspect of ray tracing is it just works. But, you know, beyond that, it's just a really brute force thing. Bullmeter says, I really like the platform and renderer setup you have. If your renderer needed to load files for shaders or something, or had to allocate a lot of stuff, would you re-implement the platform-specific functions in the renderer, or would you pass your platform API struct to the renderer initialize and use the ones your main executable implemented? I think the answer is, for the most part, I don't think a renderer should really be loading anything. So I would probably try to do that stuff with feed forward. So meaning I would want the platform independent stuff to do the loading, and I would want it to pass it to the renderer. I can't think of any reasons why you can't do that. Like, you should just be able to do that always. So that's what I would do. In terms of allocation, though, I would say that should all live inside the renderer, and the reason for that is because the renderer may need to be doing special purpose kinds of allocations. So when the renderer needs to do things like allocate texture space and stuff like that, that should be happening inside the renderer, because it's the only thing that knows what kind of memory and when that needs to happen. So I would say there's a split there. Resource loading should go through the standard pipeline because it needs to take advantage of the multi-threading and different sort of scheduling things. So you really want that to be in the platform independent part of stuff. But everything else you mentioned, I think, wants to go in the renderer. All right, I'm going to go ahead and wrap it up. We definitely have our work cut out for us tomorrow. Although everything kind of went reasonably today, we kind of have a problem of that light source. Yeah, not sure exactly how we're going to do that, but we're gonna have to think that through. So I'm going to wrap it up for now. Let's go ahead and close this down. Thank you, everyone, for joining me for the episode of Handmade Hero. It's been a pleasure coding with you, as always. If you would like to follow along the series at home, you can always pre-order the game on handmadehero.org. It comes with the source code so that you can follow along with it. I will be back here, same time, same place tomorrow to take a look at that lighting and how we're going to actually track what direction the lights go in inside the spatial partition. Or maybe we'll introduce some totally separate way of handling it. But either way, we're going to do something related to that, and I'll be back here tomorrow to do that. Until then, have fun programming, and I will see y'all on the internet. Take it easy, everybody.